This is the M4A3E Eight Sherman. Often called the Easy 8, it was the final major wartime evolution of the American Sherman tank during World War II. Production began in mid-1944, at a point when the US Panzer's Army was no longer designing tanks for theory, but for real battlefield conditions. The Easy 8 was not created to be the most heavily armored tank or the most powerful gun platform of the war. It was designed to function reliably under sustained combat, rough terrain, and constant logistical pressure. Officially designated M4A376W HVSS, this version introduced three critical changes: a 76mm gun, wet ammunition storage to reduce internal fires, and a new suspension system that transformed how the tank moved across broken ground. The horizontal volute spring suspension allowed wider tracks, lower ground pressure, and far better stability than earlier Sherman variants. This directly improved mobility in mud, snow, rubble, and soft soil, where many tanks lost momentum or became immobilized. The nickname Easy 8 did not come from comfort. It came from control, predictability, and mechanical stability under load. This tank appeared late in the war, but it represented years of accumulated engineering lessons, battlefield feedback, and industrial constraints. Every change reflected a balance between protection, mobility, production speed, and crew survival. The Easy 8 is often remembered through film and popular culture, but this video is not about legend. It is about engineering logic, system design, and operational trade-offs. Why the tank was built the way it was, what problems it was meant to solve, and what compromises it accepted to keep crews alive and units moving. My name is Marcus Reed, and this is Iron Blueprint. The Easy 8 was operated by a crew of 5. Each position was defined by function, not comfort. And every role existed to keep the tank moving, fighting, and surviving under pressure. At the front of the hull sat the driver on the left and the bow gunner on the right. The driver was responsible for movement, positioning, and terrain negotiation. The bow gunner operated the hull machine gun, assisted with navigation, and monitored the front of the vehicle for threats. Behind them, in the fighting compartment, were the loader, the gunner, and the commander. The gunner sat to the right of the main gun. His job was precision and timing. He controlled turret traverse, gun elevation, and firing. Accuracy mattered, but speed mattered more. A delayed shot could mean a missed opportunity or a fatal hit in return. The loader stood to the left of the gun. His role was physically demanding and mentally critical. He selected ammunition types, handled heavy rounds, and maintained a steady rate of fire while the tank was moving, shaking, and under stress. Above them sat the commander. The commander was not simply an observer. He coordinated movement, selected targets, communicated with other tanks, and made rapid decisions based on incomplete information. His position in the turret gave him the widest situational awareness available inside the vehicle. The internal layout of the Easy 8 reflected priorities shaped by experience. Space was allocated around the gun and ammunition first, crew second. Seating was minimal. Storage was tightly packed. Every surface served a function, whether structural, mechanical, or logistical. Wet ammunition storage was placed under the floor, lowering the center of gravity and reducing the risk of catastrophic fires. This decision influenced the entire internal arrangement, from crew posture to engine placement. Visibility inside the tank was limited. Periscopes and vision blocks provided narrow fields of view. Most situational awareness came from coordination, communication, and the commander operating with his head exposed whenever possible. The Easy 8 interior was not designed for comfort or endurance. It was designed for sustained operation in combat conditions, where clarity of roles, predictable layout, and mechanical reliability mattered more than human convenience. This internal organization allowed crews to function as a system rather than as individuals. And that system thinking defined the Easy 8. The Easy 8 Sherman was a large vehicle by World War II standards. From the front of the hull to the rear, the tank measured just over 20 feet in length. When the main gun overhang was included, the total length approached 25 feet. This extended profile affected maneuvering, but it also allowed a more balanced internal layout. The hull was just under 10 feet wide at its widest point. between the center line of each track. The width was narrower. This configuration lowered the center of gravity compared to earlier Sherman variants and reduced the risk of rollover when operating on slopes, embankments, or damaged roads. Overall height from the ground to the top of the turret was approximately 9 feet 9 inches. This made the EZ-8 taller than many contemporary tanks. The British Cromwell, for example, was significantly lower. Height increased visibility, but also made concealment more difficult. This height was not accidental. The vertical space allowed room for underfloor wet ammunition storage, larger suspension travel, and improved internal clearance for the crew. These choices directly affected survivability and long-term operational effectiveness. Fully loaded for combat, the EZ-8 weighed over 74,000 pounds. This was several thousand pounds heavier than earlier Shermans fitted with the same gun. On paper, extra weight suggested reduced mobility. In practice, the improved suspension and wider tracks distributed this weight more effectively. Ground pressure was lower than earlier models, allowing the tank to cross soft terrain without sinking or losing traction. Weight distribution was carefully managed. The engine sat at the rear. The transmission and final drives were placed at the front. Ammunition storage was moved low and central. This balance allowed the tank to cross wide ditches, climb steep slopes, and maintain stability while firing on uneven ground. The EZ-8 could climb vertical obstacles up to 2 feet high, cross trenches over 7 feet wide, and wade through shallow water without preparation. These were not extreme performance figures, but they were reliable and repeatable. This consistency mattered more than peak capability. The EZ-8 was not built to impress on a test range. It was built to perform predictably under load, with a fully equipped crew, across damaged terrain, day after day. Its dimensions and weight were the physical expression of that philosophy. The hull of the EZ-8 reflected lessons learned from earlier Sherman variants under combat conditions. Unlike some previous models that used multi-piece hull fronts, the EZ-8 featured a one-piece welded upper glacis. Removing weld seams reduced structural weak points and improved overall armor integrity. In combat, every joint was a potential failure point. The frontal armor plate was sloped at approximately 47 degrees from vertical. This was less steep than earlier Sherman variants, which initially appears counterintuitive. However, the EZ-8 compensated with thicker armor. The frontal plate measured 2.5 inches, compared to the 2 inches found on earlier models. The result was improved, effective protection, rather than a simple increase in thickness or angle. The lower front hull, which housed the transmission, used a combination of sloped and vertical armor sections. Thickness ranged from roughly 2 inches on angled surfaces to over 4 inches where the housing sat vertically. This area was heavily reinforced because damage here could immobilize the tank completely. Side armor on the hull sponsons measured approximately 1.5 inches thick. Rear armor was of similar thickness. Underfloor armor was 1 inch thick, while the top deck was thinner, reflecting the lower probability of plunging fire compared to direct hits. All armor used on the EZ-8 was homogeneous rolled steel. This single-layer construction avoided the cracking and internal spalling issues sometimes associated with face-hardened armor used by other nations. The design favored predictable failure behavior over theoretical maximum resistance. Crew survivability influenced hull design as much as protection. The EZ-8 featured enlarged driver and bowgunner hatches compared to earlier Shermans. These larger openings allowed faster escape if the tank was disabled or set on fire. As with all Sherman variants, an emergency escape hatch was also located in the hull floor. Armor on the EZ-8 was not intended to make the tank invulnerable. It was designed to manage damage, delay penetration, and give the crew time to react. The hull was a compromise between protection, weight, and manufacturability. It reflected a design philosophy focused on survival through system balance rather than armor dominance. The EZ-8 used a newly designed turret derived from the experimental T-23 medium tank. A new turret was required because the 76mm gun was longer, heavier, and generated greater recoil forces than earlier Sherman armament. The previous turret designs could not safely accommodate these loads without compromising balance and reliability. The turret was a single-piece steel casting, Armor thickness was approximately 2.5 inches around most of the turret, with a roof thickness of 1 inch. While this was slightly thinner than some earlier Sherman turrets, protection was increased through design rather than raw thickness. The key element was the gun mantlet. The mantlet was specifically designed for the 76mm M1 series gun and covered most of the turret front. It added over 3 inches of additional effective protection in the most likely direction of incoming fire. This concentrated armor where it mattered most, without increasing weight across the entire turret. The main gun fitted to the EZ-8 was the 76mm M1A1. To manage weight and balance, the barrel was shortened compared to earlier versions. Even with this reduction, the gun provided significantly improved anti-armor performance compared to the earlier 75mm weapon. Ammunition selection was critical. Standard armor-piercing rounds were effective against lightly armored targets at medium range. For heavily armored opponents, specialized high-velocity ammunition allowed the gun to penetrate thicker armor at closer distances. These rounds were limited in number and used selectively. Turret operation combined hydraulic and manual systems. Primary traverse was powered hydraulically by an electric motor located near the gunner. This allowed rapid turret rotation. A full rotation could be completed in under 20 seconds, giving the EZ-8 a significant reaction advantage over many enemy tanks. If the powered system failed, manual hand controls allowed the turret to be traversed at reduced speed. This redundancy ensured the tank remained combat capable even after mechanical damage. The commander had override control of the turret, allowing him to reposition the gun independently if necessary. This ensured command authority was maintained even under chaotic conditions. Inside the turret, space was limited. Seats for the commander and loader were attached directly to the turret ring, rotating with the gun. The turret basket was partially cut away, reducing weight and allowing more freedom of movement, but increasing physical strain on the crew. The turret of the EZ-8 was not designed for comfort or prolonged exposure. It was designed for speed, control, and survivability in short, violent engagements. Every element reflected the same philosophy seen throughout the tank. Concentrate capability where it matters. Accept compromise everywhere else. The EZ-8 was powered by the Ford GAA engine. This was an 8-cylinder V-shaped gasoline engine with a displacement of 18 liters. The engine used liquid cooling and aluminum construction to reduce overall weight while maintaining structural strength. Maximum rated output was approximately 500 horsepower. After powering auxiliary systems and passing through the drivetrain, roughly 450 horsepower was available to move the tank. This power level did not make the EZ-8 fast by modern standards. Top speed was around 26 miles per hour. What mattered more was consistent torque delivery and mechanical reliability under sustained load. The engine was mounted at the rear of the hull. Power was transmitted forward through a drive shaft that ran beneath the fighting compartment to the transmission at the front of the tank. This layout increased internal space and allowed ammunition to be stored low in the hull, improving stability and crew safety. The transmission, differential, and final drives were combined into a single integrated unit known as the Powertrain. This entire assembly could be removed and replaced as one piece. If a major mechanical failure occurred, field maintenance crews did not repair individual components. They swapped the entire unit. This dramatically reduced repair time and returned damaged tanks to service faster. The trade-off was maneuverability. The transmission design did not allow the tracks to rotate in opposite directions while in neutral. As a result, the EZ-8 could not pivot in place like some other tanks. It required a wide turning radius to change direction. This limitation was accepted in exchange for mechanical simplicity, durability, and ease of maintenance. From an engineering perspective, the EZ-8 Powertrain prioritized uptime over agility. It favored systems that could be repaired quickly, replaced easily, and operated reliably by crews with limited training under combat conditions. The engine and powertrain were not designed to win races. They were designed to keep tanks moving, even when parts failed and conditions were poor. That reliability was one of the EZ-8's most important weapons. The EZ-8 carried its fuel in multiple internal tanks, distributed within the hull. In total, the system held approximately 168 gallons of gasoline. This provided an operational range of around 100 miles under typical combat conditions. Fuel consumption averaged roughly 0.6 gallons per mile. Actual range varied depending on terrain, speed, load, and tactical behavior. Continuous maneuvering, soft ground, and frequent stops reduced endurance quickly. Fuel storage was designed around balance and safety, rather than maximum capacity. Tanks were positioned to avoid excessive concentration in any one area. This reduced the risk of catastrophic loss from a single penetration and helped maintain predictable weight distribution as fuel was consumed. Gasoline engines carried inherent fire risk. The EZ-8 did not eliminate this danger, but design choices limited exposure. Fuel lines were routed away from the fighting compartment, where possible, and armored separation reduced the chance of immediate ignition following penetration. Operational doctrine treated fuel as a logistical constraint rather than a tactical advantage. The EZ-8 was not intended to conduct long, independent advances. It was designed to operate within a supply network supported by fuel trucks and forward depots. Continuous movement depended on steady resupply rather than onboard endurance. This approach reflected industrial reality. The United States could deliver fuel more reliably than it could redesign engines mid-war. Engineering decisions aligned with logistics rather than attempting to overcome them. Fuel capacity and range were sufficient, not exceptional. What mattered was that the tank could be kept moving day after day. As long as supply lines held, the EZ-8 did not win battles through range. It remained effective because fuel consumption, resupply, and operational planning were treated as parts of the same system. The EZ-8 was driven using a control system designed for reliability rather than finesse. The driver operated the tank using a manual gearbox with 5 forward gears and 1 reverse. Gear selection required coordination between clutch control and throttle input, similar in principle to a civilian manual transmission, but under far heavier loads. 2 pedals were positioned in front of the driver. The clutch pedal sat on the left. The accelerator pedal was on the right. Braking and steering were not handled by foot pedals, but by 2 steering levers positioned between the driver's legs. Each steering lever controlled power and braking for one track. Pulling a lever back applied braking force to the corresponding track. Reducing power on one side while maintaining power on the other caused the tank to turn. The sharper the imbalance, the tighter the turn. Pulling both levers back fully brought the tank to a stop. Pushing both levers forward allowed full power to both tracks. This system required physical strength and constant attention. Fine control was possible, but it demanded experience. Overcorrection could lead to abrupt turns, loss of traction, or excessive track wear, especially on soft ground. Because the transmission did not allow neutral steering, the EZ-8 could not rotate in place. All turns required forward or reverse motion. This increased the turning radius and limited maneuverability in confined spaces. Handling characteristics were predictable rather than agile. The tank responded consistently to input, but slowly. Momentum mattered. Sudden changes in direction were discouraged by both mechanical limits and crew workload. Driver training emphasized smooth control, anticipation, and terrain awareness. Poor handling increased mechanical stress and raised the risk of immobilization, even without enemy action. The EZ-8 did not reward aggressive driving. It rewarded disciplined movement. Vehicle handling was shaped by engineering priorities focused on durability, ease of maintenance, and repeatable performance. These traits aligned with operational doctrine that valued steady advances over rapid maneuvers. The driver was not expected to perform acrobatics. He was expected to keep the tank moving, positioned, and operational under constant pressure. That expectation defined how the EZ-8 handled on the battlefield. The EZ-8 earned its nickname primarily because of its suspension system. This variant introduced the horizontal volute spring suspension, commonly known as HVSS. Earlier Sherman models used vertical volute spring suspension, which limited wheel travel and restricted track width. HVSS fundamentally changed how the tank interacted with the ground. In this system, the volute springs were mounted horizontally between paired road wheels. As the suspension compressed under load, forces were distributed laterally across the bogie assembly, rather than vertically into a single spring stack. This allowed smoother movement over uneven terrain and reduced shock transfer to the hull. Each side of the tank used 3 bogie units, Each bogie carried 4 road wheels arranged in pairs. Above the bogies were return rollers that supported the upper run of the track and maintained alignment during movement. The most important advantage of HVSS was track width. The Easy 8 could be fitted with tracks significantly wider than earlier Shermans. Wider tracks spread the tank's weight over a larger surface area, reducing ground pressure. This improved mobility on soft soil, mud, snow, and rubble. Lower ground pressure meant the tank was less likely to bog down or lose traction, where earlier variants struggled. Ride quality improved as well. The suspension absorbed terrain irregularities more effectively, reducing crew fatigue and mechanical stress. This mattered during long advances, where constant vibration degraded accuracy, endurance, and equipment reliability. The running gear was designed for durability rather than refinement. Components were large, robust, and easy to service. Track types varied depending on operational needs, but most wartime Easy 8s used all steel tracks, as damage to roads was not a primary concern during offensive operations. Maintenance access was straightforward. Bogie units could be removed and replaced without dismantling the entire suspension system. This reduced downtime and kept tanks operational closer to the front. The suspension did not make the Easy 8 fast or agile. It made the tank predictable, stable, and capable of sustained movement across damaged terrain. That consistency allowed commanders to plan operations around what the tank could reliably do, rather than what it might achieve under ideal conditions. HVSS was not an upgrade for comfort. It was an upgrade for control, endurance, and survivability. It was one of the most important mechanical changes ever made to the Sherman platform. The primary weapon of the Easy 8 was the 76mm M1 series gun. This gun was introduced to address the limitations of earlier Sherman armament when facing heavier German armor. It offered higher muzzle velocity and improved penetration compared to the 75mm gun used on earlier variants. The barrel length of the M1A1 variant was just under 12 feet. This length balanced ballistic performance with turret space and recoil management. A longer gun would have improved penetration further, but at the cost of weight, balance, and reliability. The Easy 8 carried approximately 71 rounds of 76mm ammunition. Ammunition types were selected based on expected targets, rather than maximum lethality. Against lightly armored vehicles, infantry positions, or field fortifications, standard armor-piercing rounds were used. These offered reliable performance and predictable behavior. When facing heavily armored targets, specialized high-velocity ammunition was available. These rounds used dense penetrators designed to defeat thicker armor at shorter ranges. Supplies were limited, and their use was carefully controlled. This reflected operational reality. The Easy 8 was not intended to duel heavy tanks head-on whenever possible. Doctrine emphasized maneuver, coordination, and combined arms rather than direct confrontation. Secondary armament supported the main gun. Inside the turret, a 30 caliber machine gun was mounted coaxially with the main gun. Another 30 caliber machine gun was mounted in the hull front, operated by the bow gunner. A 50 caliber heavy machine gun was mounted on the turret roof. This weapon was effective against infantry, lightly armored vehicles, and low-flying aircraft. However, its use exposed the crew member operating it, who often had to stand partially outside the turret under fire. Armament on the Easy 8 was not excessive. It was sufficient, flexible, and integrated into the overall system of the tank. Firepower was one part of survivability, but it was never treated as a standalone solution. The Easy 8 relied on coordination, ammunition, selection, and tactical discipline as much as on raw weapon performance. One of the most important design changes in the Easy 8 was wet ammunition stowage. This feature was indicated by the letter W in the tank's designation. It directly addressed one of the most lethal weaknesses of earlier Sherman variants: ammunition fires after penetration. In earlier models, ammunition was stored higher in the hull and along the side sponsons. When these areas were penetrated, propellant charges could ignite, leading to rapid internal fires and catastrophic loss of the crew. The Easy 8 moved main ammunition storage to the hull floor. Rounds were placed in armored bins below the fighting compartment. These bins were double-walled, with the space between the walls filled with a liquid mixture. The liquid absorbed heat and suppressed ignition if the bin was penetrated. If a round was struck, the liquid flooded the compartment holding the ammunition, drastically reducing the chance of fire spreading. This change had measurable effects. Without wet stowage, Sherman tanks were likely to burn after penetration in the majority of cases. With wet stowage, the probability dropped dramatically. Penetration no longer guaranteed immediate loss of the vehicle or crew. This did not make the Easy 8 immune to destruction. It changed the outcome window. Crews gained time. Time to evacuate. Time to fight fires. Time to survive hits that would previously have been fatal. Wet stowage also influenced internal layout. By placing ammunition low in the hull, the center of gravity was reduced. This improved stability while moving and firing. It also freed space in the side sponsons, reducing secondary hazards inside the fighting compartment. Crew survivability was not treated as an abstract concept. It was addressed through specific mechanical decisions. Armor thickness, layout, ammunition placement, and escape access were considered together rather than in isolation. The Easy-8 did not rely on armor alone to protect its crew. It relied on damage management. Wet ammunition stowage was one of the clearest expressions of that philosophy. The tank was designed not just to resist penetration, but to remain survivable after being hit. Effective firepower depends on seeing the battlefield clearly and coordinating crew actions under pressure. The Easy-8 relied on a combination of optical sights, periscopes, and crew coordination rather than complex fire control automation. Each crew member had limited direct visibility. The driver and bow gunner were equipped with rotatable periscopes that allowed observation while buttoned up. These provided narrow fields of view and required constant adjustment to maintain situational awareness. Inside the turret, the commander had the best overall visibility. His cupola was fitted with multiple vision blocks, providing a continuous 360-degree view of the surroundings. This allowed him to detect threats, identify targets, and coordinate movement while the tank was under armor. The gunner used two primary sighting systems. For precision aiming, a telescopic sight was mounted alongside the main gun. This provided magnification and a narrow field of view for accurate engagement at distance. For general observation and alignment, a periscope sight was also available. This allowed the gunner to remain protected while tracking targets and adjusting fire. Fire control was manual. There were no range-finding systems or ballistic computers. Distance estimation relied on training, experience, and the commander's judgment. Target engagement was a coordinated process rather than an automated one. Communication was critical. The commander identified targets and issued firing orders. The gunner laid the gun and confirmed alignment. The loader selected ammunition and maintained the firing cycle. Each step depended on clear verbal commands and disciplined execution. This system favored reliability over complexity. While less precise than later fire control systems, it was robust and resistant to damage. Even if optics were degraded or power systems failed, the tank could continue to fight using backup methods. Vision and fire control on the Easy-8 reflected its overall design philosophy. The tank did not rely on advanced technology to compensate for uncertainty. It relied on trained crews, clear roles, and predictable mechanical systems. In combat, awareness and coordination mattered as much as armor and firepower. Combat effectiveness in the Easy-8 depended on disciplined crew coordination rather than individual action. Direct fire followed a clear sequence of responsibility. The commander was responsible for target detection and engagement decisions. He operated with his head exposed whenever conditions allowed, using binoculars to scan terrain, identify threats, and prioritize targets. Situational awareness began at this position. Once a target was identified, the commander issued verbal instructions to the crew. These included target direction, type, and urgency. Clear communication reduced hesitation and prevented wasted movement. The gunner responded by traversing the turret and elevating the main gun. When the gun was aligned and ready to fire, he confirmed status verbally. Precision mattered, but speed was critical. Delays increased exposure to enemy fire. The loader selected the appropriate ammunition based on the commander's order. He removed rounds from storage, handled them under movement and vibration, and maintained a steady firing rhythm. Ammunition choice directly affected engagement outcome. Once alignment was confirmed, the commander gave the final firing command. The gunner fired the main gun using either the trigger control or the foot switch mounted on the turret floor. After firing, the cycle repeated. The gunner reacquired the target. The loader prepared the next round. The commander assessed the effect of the shot and adjusted instructions as needed. This process required constant coordination. Noise, vibration, smoke, and limited visibility made communication difficult. Crews relied on standardized commands and practice routines to function under stress. There was no automation to compensate for confusion. Fire control depended on human judgment, training, and discipline. Errors in communication could result in missed shots, wasted ammunition, or exposure to return fire. The Easy-8 did not attempt to simplify combat through technology. It simplified it through procedure. Each crew member understood his role. Each action followed a predictable sequence. This reduced cognitive load and allowed the crew to function effectively, even when conditions deteriorated. Direct fire in the Easy-8 was not about speed alone. It was about controlled action under pressure, where coordination turned mechanical capability into combat effectiveness. Starting the Easy-8 followed a deliberate and methodical process. The procedure was designed to protect the engine, prevent mechanical damage, and ensure reliable operation under field conditions. Before ignition, the driver set the transmission to neutral and engaged the battery master switch. This ensured electrical power was available to all starting systems without loading the drivetrain. The throttle was partially opened, using the hand control. This provided sufficient airflow and fuel for ignition without overstressing the engine during startup. The ignition switch was then set to the active position. If the engine was cold, the driver used the manual primer to introduce fuel directly into the intake system. 1 to 3 strokes were typically sufficient. The starter control was engaged. Once the engine fired, the driver monitored engine behavior closely. If the engine did not continue running smoothly, additional priming was applied and the start sequence repeated. This process required attention and experience. Overpriming could flood the engine. Insufficient priming could prevent ignition. Starting the engine was not automatic. It relied on the driver's judgment. Once running, the engine was allowed to stabilize before movement. Oil pressure, temperature, and electrical output were checked. Sudden acceleration was avoided to reduce mechanical stress. To move the tank, the driver depressed the clutch, selected the desired gear, and gradually released the clutch while applying throttle. Smooth engagement was essential to prevent drivetrain shock. Engine operation during combat emphasized consistency. The Ford GAA was not designed for aggressive throttle changes. Maintaining steady engine speed reduced wear and improved reliability. Abrupt inputs increased the risk of overheating and mechanical failure. Auxiliary electrical power could be supplied by a generator located in the rear of the hull. This allowed batteries to be charged and systems to operate without running the main engine, reducing fuel consumption and acoustic signature when stationary. Engine operation in the Easy-8 was not about performance. It was about reliability, predictability, and sustained function. Proper startup and disciplined handling extended engine life and kept the tank operational under continuous use. The system rewarded crews who treated the engine as a critical resource rather than a disposable component. The Easy-8 was produced late in the Second World War, but it represented the most complete expression of the Sherman design philosophy. Between 1944 and 1945, just over 2,600 Easy-8s were built. They entered service at a time when battlefield conditions were already well understood and design priorities had shifted from theory to proven necessity. The Easy-8 was not designed to dominate through armor thickness or firepower alone. It was designed to function as a balanced system. Every major design choice reflected trade-offs between protection, mobility, production speed, and crew survivability. Thicker armor was applied selectively. Firepower was improved without overwhelming the turret. Mobility was enhanced through suspension and track design, rather than raw engine output. Most importantly, survivability was addressed through damage management, rather than invulnerability. Wet ammunition stowage, predictable mechanical systems, redundant controls, and repair-friendly components gave crews time and options after being hit. The tank was designed to stay operational, or at least survivable, even when damaged. This approach aligned with industrial reality. The United States could produce tanks in large numbers, supply fuel reliably, and replace damaged vehicles quickly. The Easy-8 fit into this system rather than attempting to overcome it through extreme design. After the war, Shermans continued to serve across the world. They were modified, rebuilt, and adapted by many armies. Some remained in frontline service for decades. The final Shermans were not retired until the early 21st century. This longevity was not accidental. It was the result of engineering choices that favored simplicity, accessibility, and adaptability over specialization. The Easy-8 did not win battles by being the best tank on paper. It worked because it was reliable, maintainable, and survivable within a larger operational system. That is its legacy, not as a myth, not as a symbol, but as a machine built to function under pressure. My name is Marcus Reed, and this is Iron Blueprint.